Hey, this is Mr. Beckstrom, and I want to go over the second part of the final exam review. So starting with questions 5 here. This says solve the following equation, write the answer in terms of the natural logarithm. That's the ln. So this one says e to the 9x is equal to 3. So I'm going to go ahead and open up my whiteboard, and I can just write that one easily enough. Oops. So e to the 9x is equal to 3. So remember, a good tool that we have when we have variables in the exponent position is to multiply each side by either the log or the natural log. In this case, there's two reasons why we want to do it by the natural log. The first is we have e, and e and natural log are inverse functions of each other, so they cancel each other out. So that'll be real nice in this case. And the other reason is because the problem asks us to put the answer in terms of the natural log. So it'd be pretty hard to convert it from log to natural log later. So I'm going to take the natural log of both sides. So the natural log of e to the 9x is equal to the natural log of 3. This cancels out, just leaving with 9x is equal to the natural log of 3. And finally, we're just going to divide both sides by 9. So we get x is equal to the natural log of 3, all divided by 9. So that should be our answer. So going back up here, I have natural log of 3 divided by 9. Alright, so that was an easy question. Hey, the next one says, solve the system of equations if the system has no solution. Say that it is inconsistent. Alright, so we don't know right now if this is a consistent set of equations or an inconsistent set. Remember, we're talking about two lines. So if those lines intersect, then we have a consistent set and we'll have a solution. If those two lines are parallel, we'll have an inconsistent set. And if they happen to be the same line, which means they are parallel and the same line, then it would be a dependent set. But we don't know that until we work it out here. So what I'm going to go ahead and do is copy this over to my whiteboard. Hopefully it comes over the first time. There it is. Oh, did it twice. Alright, so there's our set of equations. So the first thing that I want to do when I'm dealing with fractions and equations is I want to multiply each equation by the LCD of that equation, the least common denominator. So the first equation would be 10, because that's the smallest number that both 2 and 5 divide into. And in the second one here, that would be 30, because that's the smallest number that both 5 and 6 divide into. And one way to check is you take the larger number and you keep taking multiples of it until the smaller number will divide into it. So for example, if we took 6, 5 does not divide into 6 evenly, so then we take 12, 5 doesn't go to 12 evenly, then we take 18. We keep doing that. Finally, when we get up to 30, 30 would be the first number that 5 divides into. You can do the same thing up here. But so this first one here, I want to multiply the entire thing by 10. So that's going to end up giving me, let me just kind of, I'll do it up here. So this whole thing by 10. And this whole thing I want to multiply by 30. So when I multiply the top by 10, so 10 times 1/2 is just 5, or 10 over 2. So 5x plus 1/5 of 10 is 2, so that's plus 2y. It's going to be equal to 10 times 4, which is 40. And the second one is, so 30 divided by 6 is going to be 5. So 5x. And then 30 times 2 is 60, and 60 divided by 5 is 12. So minus 12y is equal to negative 30. Now I'm going to go ahead and do this one by elimination by addition, which means I'm going to try to multiply one of these equations by something that will allow me to add them and eliminate one of my variables. In this case, if I just multiply the second equation by a negative, so that turns that negative, this turns this positive, and turns that positive, which changes the sign of everything. Now I'm going to add these two equations together. So these will cancel out, and I'm just left with 14y is equal to 70, and therefore y is equal to, it almost looks like a greater than symbol, y is equal to 70 divided by 14, which is 5. So that's easily gives me my 5, or my y value. And then I can just come up here and either one of these equations, plug that 5 in. I'll do it with the first equation. So I'm going to say 5x plus 2 times my 5 that I got for the y is equal to 40. And that should be pretty easy to solve. So 5x is equal to 2 times 5 is 10, and then subtract the 10 from both sides, so you're going to get 30. And x is equal to 6. So I got y is equal to 5, and x is equal to 6. And if I wanted to go back in there, I could check those. All right, so x is equal to 6, and y is equal to 5. So this is a consistent solution, which means that these lines are not parallel because they intersect each other at the 0.65. All right, number 7 here. It says graph the following function using the techniques of shifting, compressing, stretching, and or reflecting. Start with the graph of the basic function shown to the right. Find the domain and the range of the function. This is h of x is equal to the square root of x plus 3. So remember what happens there when we look at our x. If we replace x with an x plus something, it's going to move it to the left by that many units. So plus moves it to the left, minus moves it to the right. So I'm going to look for the graph that moves this to the left 3 units, and it looks like it's B right there. And that's pretty much the same for exponential functions, for polynomial functions, many of the ones that we do. The domain is what are all of the x values that will go into this. Now I'm going to kind of use a little bit of visual reasoning as well as a mathematical reasoning. So my visual reading, since this is the graph, says, look, I have x values at -3 all the way up to infinity. And I can put -3 in there because I can find the square root of -3 plus 3, which is 0, which is equal to 0. So just from looking at that, I can say with a pretty good confidence level that the domain is from -3 to infinity, but let's go ahead and just mathematically show that as well, just in case I wasn't 100% convinced. So I have the square root of x plus 3, so let me go back to alright, so if I'm looking at the function y is equal to the square root of x plus 3. Remember, we as far as the real numbers, we can't have the square root of a negative number. That means that whatever's inside here, the x plus 3, has to be greater than or equal to 0. So I can set up this inequality like this. Whatever's inside this radical has to be greater than or equal to 0 because we can't take the square root of a negative number. So now if I just subtract 3 from both sides, I get x is greater than or equal to -3, which is what I came up before. And in interval notation, that means that I include the 3, so I write the bracket, and I go all the way up to infinity. And we always use a parenthesis. That wasn't a very good parenthesis, but we always use a parenthesis with infinity. Alright, so let's put that in there. So -3, comma, infinity. Alright. Now my range, I'm going to need a little bit more of a visual explanation for this. So I'm just looking at all the possible y values in there. And we can see that we're not going to get any y values that are negative either. There's nothing below the x-axis. So there's no negative y values. Although we do have a y value at 0. So this is just going to go from 0 to positive infinity in the y direction. So we include 0, and we go all the way up to positive infinity, and that's more just by looking at the graph. It's a little bit harder to show like we did with the domain. Alright, not too bad. Next question says, analyze the graph of the function x squared plus 6x plus 8. And if needed, first write the function as a single rational expression, then factor the numerator and denominator, select the correct choice below, and if necessary, fill in the answer box to complete your choice. Alright, so it looks like the top can be factored into x plus 4 times x plus 2, because 2 times 4 is 8 and 2 plus 4 is 6. So I'm going to go ahead and put that in there. X plus 4 times x plus 2, and this is going to be all divided by x plus 4. So they just want us to write this out in factored form. And the domain of the function, so they have this in set notation here. Remember, the two main ways we show domains and ranges are in interval and in set notation. So set notation reads x such that the little vertical line means such that, and we're going to say x is not equal to something or x is greater than something. In this case, remember, for the domain, it's all the x values we can put into this function while it's still defined and in real numbers. So in this case, when we have a fraction like this, the only thing that we can't have in there is some x value that's going to make our denominator equal to 0. Because we can't have a denominator equal to 0. So it's going to be every x value except for, and hopefully you can see that, is -4. Because if you put a -4 in there, -4 plus +4 is 0, and then we're dividing by a 0, and that's no good in the math world. So so that x is not equal to -4. And that's the same thing as putting an interval notation from -infinity to -4, and then from -4 to positive infinity. Although in this case, when we're just eliminating like a single value, it's a lot quicker to put it in the set notation. All right. Now it says write it in lowest terms. Select the correct choice below. So we can cancel out that x plus 4 on the top and the bottom, and we're just going to be left with an x plus 2. All right, the next thing it says, locate the intercepts of the graph. Select the correct choice below, and if necessary, fill in the answer box to complete your choice. All right, so to find our y-intercept, we're going to let our x's equal 0. So if I let my x's equal 0 here, I am going to have, this is going to be 0 plus 4, which is 4, times 2, which is 8, over 4, which is 2. So I have a y-intercept of 2. I can do that just simply by putting in a 0 for x. And to solve for the x-intercept, I'm going to put in a 0 for y. Now notice that we've been able to reduce this function down to this right here. So I can just set this x plus 2 equal to y and subtract 2 from both sides, and I'm going to get, excuse me, set this x plus 2 equal to 0. And then I can subtract 2 from both sides, so my x-intercept will be equal to -2. Okay. And now it says determine the behavior of the graph R at the x-intercepts. Select the correct choice below, and if necessary, fill in the answer boxes to complete your choice. So we know that we only have the one factor here, which is x plus 2. And it's only to the first power, so it's not squared or cubed or anything like that. So we know it's going to cross the x-axis at -2. So it looks like it's just going to be this one right here. The graph will cross the x-axis at -2. And that's the only x-intercept, and it crosses because the multiplicity is odd, because that x plus 2 factor is to the first power. All right, determine the vertical asymptotes if one exists. Select the correct choice below, and if necessary, fill in the answer box to complete your choice. So it might be very tempting to say that we have a vertical asymptote at -4, because that makes this denominator equal to 0. What we have to remember is that if we put a -4 in this function, we're going to end up getting 0 over 0, which is an indeterminate form, which very often means that we can factor something out. So in order to calculate the vertical asymptotes, often it's good to graph this function. And remember, this function is identical to this function, except for the fact that there's a hole in the graph at -4. So this is really just a straight line with a hole where x is equal to -4. Therefore, there's no vertical asymptotes here, because a vertical asymptote is that vertical line that the graph will approach from one way or the other or both ways. So there's no vertical asymptote. All right, determine the behavior of the graph on either side of the vertical asymptotes if one exists. Select the correct choice below, and if necessary, fill in the answer boxes to complete your choice. Once again, there is no vertical asymptote. Determine the horizontal or oblique asymptote if one exists. Select the correct choice below, and if necessary, fill in the box to complete your choice. And if there is a horizontal asymptote, it's definitely not going to be for a straight line. It really needs to be something that's different function than that, because what we're doing to find the horizontal asymptote is we're letting the x values either go to positive infinity or negative infinity, and we're seeing if the y values are approaching some constant, in which case they're not, because in the function of y equals x plus 2, as you let x approach positive infinity, your y value is getting towards positive infinity, and if you let x approach negative infinity, your y value goes towards negative infinity. And you can just plug in really large numbers or really small numbers to kind of check that. So no horizontal asymptote. The times that we do have a horizontal or oblique asymptote is if after factoring we still have expressions on both the top and the bottom polynomial expressions. All right. Determine the points, if any, at which the graph of R intersects the horizontal or oblique. There is no horizontal asymptote. All right. And to graph R using a graphing utility, determine an appropriate viewing window necessary to obtain a complete graph. Choose the correct answer below. in here, this is just a straight line. It intersects at 2, so just a standard viewing would be fine. So for your x's -10 to +10, for your y's -10 to +10, that'd be fine to get the line. All right. And using the result from the previous steps to graph R, choose the correct graph below. Remember, it's the graph of x plus 2, so it goes through the 2 on the y-axis there, like this one, and it has a slope of 1/1, so it's going to be that one right there. All right. Last problem on the review. Find the complex zeros of the polynomial function and write it in factored form. So we're given a polynomial of degree 3, and we really need to use our rational root theorem in order to hopefully get one of these roots, so we can get this down to at least a quadratic. So what I'm going to do is I'm going to go ahead and put this function in my calculator. So x cubed minus 13x squared plus 59x minus 87. All right, and enter. All right, so now remember, hopefully you do, that when we're finding those possible rational roots, that we can take all the factors of the last of the constant term, and we can divide it by all of the factors of the first term. All the factors of this last term, we'll go ahead and break that 87 down, and then 1 is just 1, so everything's going to be divided by 1 or -1, so we'll just look at all the positive and negative factors of 87. So doing that, I go to 87, and since the digits add up to 15, I know that we can factor a 3 out of there. So 87 divided by 3 is 29, and 29 is a prime number, so that's it right there. So it's going to be the possible factors of 87 are plus or minus 1, plus or minus 3, so plus 3 and minus 3, plus or minus 29, and finally plus or minus 87. All right, and since I already have that in there in my y equals function, remember what happens is if I evaluate the function at that number and I get 0, that means that it's a root of my function. So that's what I'm going to do here. I'm going to go ahead and go to my table, and we're going to start with 1. Nope, not a root. -1. Nope. 3. Oh, 3 is a root. -3. It's not a root. 29. Nope. -29. Nope. And 87. Nope. And -87. Nope. So the only one that comes out to be a root is the 3, which is fine. That'll get us down to a quadratic. And that's the only possible rational roots, which means my other 2 roots are either going to have to be irrational or they're going to have to be imaginary. That's my only choice. So I know that I'm not going to be able to factor that polynomial easily once I get it. But once again, we have 3 as one of our roots, so I'm going to use synthetic division to break that that polynomial down to a second-degree polynomial. So 3, and let's go back up to it. So now I put down the coefficients. So that's 1, -13. I can't remember 4 numbers in a row anymore. 1, negative 13, and the other two were 59 and negative 87. All right, and 59 and negative 87. All right, so I should get a 0 at the end here. If I didn't, then I did something wrong. So I bring down the 1. 1 times 3 is 3. 3 plus negative 13 is negative 10. Negative 10 times 3 is negative 30. Negative 30 plus 59 is 29. 29 times 3 is 87. And 87 plus negative 87 is sure enough 0. So I'm going to get a second degree polynomial, quadratic, of x squared minus 10x plus 29. Oops, plus 29. So if I put it like this, I know I have factored out a x minus 3. Remember, it's the opposite sign of the 0, because when we set this equal to 0, we need to get that 3 back. All right, so now I've got to deal with this thing. And like we've already said, we're not going to be able to factor it, because if we were, it would have showed up in our rational root check there. So in this case, what I'm going to do is I'm going to use the quadratic formula. So here my a is equal to 1, my b is equal to negative 10, and my c is equal to 29. All right, so it's negative b, so that's going to be 10, because it's a negative of a negative 10, plus or minus the square root of b squared, that's 100, minus 4 times a times c. So 4 times 29, 4 times 29 is 116. So minus 116. And there we can already see that the discriminant is going to be negative, meaning that we're going to get imaginary solutions here. All over 2a. All over 2a. All right, so this is going to be 10 plus or minus. Now remember, this is going to be 100 minus 116, so that's going to be the square root of negative 16, which is going to be 4i, right? Because the square root of 16 is 4, and the square root of negative 1 is I, so we can just write that as 4i, all over 2, which is going to be equal to, I can just break this up into two fractions, so 10 divided by 2 is 5, and 4 divided by 2 is 2. So 5 plus or minus 2i. So there are my 3 complex zeros of the function. I have 3, 5 plus 2i, and 5 minus 2i. I wish I messed up somewhere. 3, 5 plus 2i, 5 minus 2i. Simplify your answer, use radicals. Good. That's it. All right. Oh, we have different parts. Use the complex zeros to factor f. So remember, we're just going to do x minus 3. That was for the 0 of 3. And we're going to do the same kind of thing here. So x minus 5. And remember, let me just show you real quick here. Let me go back. Oops. Go back to this. And I'll move up here. If I have x minus 5 plus 2i, that's going to simplify after I distribute that negative to x plus, x minus 5 minus 2i. And if I do the x minus f minus 2i, I'll get a similar result of x minus 5 plus 2i. So those are going to be simplified versions of the factored zeros for my imaginary numbers there. Alright, so let's go back up to here. So x minus 5i minus 2i. And finally, x minus 5 plus 2i. Should be alright. Alright, and that's the whole review. So we'll have the review Thursday at 6 o'clock on the 16th. And let me know if you have any questions. Thanks, and good luck on the final exam.